Hello everyone. Let me begin with a question. When you cook food in a pressure cooker, why does the steam stop escaping after some time, even though heating continues? That's because the system has reached a balance, a steady state we call equilibrium.
In chemistry, an equilibrium mixture is one where reactants and products coexist and their concentrations remain constant with time. This does not mean reactions have stopped. It means that the forward reaction and the backward reaction are happening at the same rate. Chemists have always been curious, how are these concentrations related at equilibrium? This is where the law of chemical equilibrium comes in, giving us a powerful mathematical relationship. Back in 1864, two Norwegian chemists, Goldberg and Wager, proposed the law of mass action. According to this law, the rate of a chemical reaction is proportional to the product of the active masses, that is, the concentrations of the reactants. From this, the equilibrium constant, symbol Kc, was introduced. For a general reaction, A plus B gives C plus D. At equilibrium, the expression is Kc equals concentration of C multiplied by concentration of D, divided by concentration of A multiplied by concentration of B. This ratio stays constant at a fixed temperature, regardless of the starting amounts of reactants or products. Isn't that fascinating? No matter how you start, the system always settles into the same balance. To see this in action, let's take the reaction between hydrogen gas and iodine gas forming hydrogen iodide gas at 731 Kelvin. Whether you begin with hydrogen and iodine together or with hydrogen iodide alone, the reaction mixture always stabilizes to the same ratio of concentrations. At equilibrium, the constant expression is written as Kc equals concentration of Hi squared, divided by concentration of H2 multiplied by concentration of I2. Experiments measured these concentrations and, when substituted, they gave the same constant value every time. This proves that equilibrium is not guesswork. It can be measured and predicted. Let us now generalize the equilibrium constant. For any reaction of the type small aa plus small bb gives small cc plus small dd, the equilibrium constant is written as Kc equals concentration of C raised to the power C multiplied by concentration of D raised to the power D, divided by concentration of A raised to the power A and concentration of B raised to the power B. The exponents are nothing but the stoichiometric coefficients from the balanced equation. If we reverse the reaction, the equilibrium constant becomes 1 by Kc. If we multiply the coefficients by a factor, the new Kc is raised to that same power. This shows that equilibrium constants are tied very precisely to how the reaction equation is written. Let's calculate Kc with an example. Consider the synthesis of ammonia. Nitrogen gas plus 3 hydrogen gas molecules form 2 ammonia gas molecules. The expression is Kc equals concentration of NH3 squared divided by concentration of N2 multiplied by concentration of H2 cubed. Suppose at equilibrium, the concentrations are nitrogen equal to 1.5 times 10 to the power minus 2 molar, hydrogen equal to 3.0 times 10 to the power minus 2 molar, and ammonia equal to 1.2 times 10 to the power minus 2 molar. Substituting these values, we get Kc equal to about 3.55 times 10 to the power 2. This numerical value shows that, under those conditions, ammonia formation is quite favorable. Now, a very important point, equilibrium constants change if we rewrite the balanced equation differently. For example, if instead of writing H2 plus I2 gives 2 Hi, we write it as half H2 plus half I2 gives 1 Hi, the expression for Kc becomes the square root of the original value. Similarly, the equilibrium constant for the reverse reaction is simply 1 divided by Kc. To generalize, forward reaction has Kc, reverse has 1 by Kc, and if the coefficients are multiplied by n, then the new constant becomes Kc raised to the power n, A neat summary of these relations is shown in your table, which helps you avoid common mistakes while solving problems. Finally, let's understand why Kc is so important. A very large value of Kc means the equilibrium is strongly product favored, while a very small value means it is reactant favored. This helps chemists predict whether a reaction will go nearly to completion or stay largely unreacted. Industrial processes like the Hubbard synthesis of ammonia and the manufacture of esters rely on manipulating conditions to achieve the best Kc values. Remember, Kc depends only on temperature, not on concentrations or pressures directly. It acts like a thermometer of reaction extent, guiding us to predict and control chemical processes. So to sum up, the law of chemical equilibrium gives us a mathematical key to unlock the balance between reactants and products. The equilibrium constant Kc tells us how far a reaction goes, whether it favors products or reactants, and helps us design better conditions for chemical industries. I hope this session made you see equilibrium not just as an abstract ratio, but as a practical, powerful tool connecting theory to real-world chemistry. Until next time, keep observing. Equilibrium is everywhere, from the fizz in your soda to the gases in our atmosphere.